In 1961, at the tense height of the Cold War, the Soviet Union sent Yuri Gagarin into orbit and made him the first human in space. The United States responded weeks later with Alan Shepard's brief suborbital flight, just 15 minutes above the atmosphere and back. He was hailed as a national hero, but President John F. Kennedy understood what this meant. If America wanted to pull ahead in space, a short hop would not be enough. So, standing before Congress, Kennedy set an audacious objective. The United States, he declared, should commit itself to landing a man on the moon and bringing him safely home before the decade was over. At that moment, the US had barely a quarter of an hour of human spaceflight experience. No one knew if such a mission was technically possible, let alone achievable in less than 9 years. What followed would be one of the most complex engineering, scientific, and operational efforts in history, a story of ingenuity, risk, loss, and triumph. It became known as the Apollo program. Before anyone could design the spacecraft that would carry astronauts to the lunar surface, NASA had to resolve a fundamental problem: how to get to the moon. Several mission profiles were debated. Among the key figures in these discussions was Wernher von Braun, NASA's leading rocket engineer. During the Second World War, von Braun had led development of Nazi Germany's V-2 ballistic missile, the first long-range guided rocket weapon. After the war, he was brought to the United States to work on American missile and space projects, and in 1960 he became the first director of NASA's Marshall Space Flight Center. The most straightforward concept was a massive, single spacecraft that would launch from Earth, land on the moon, and then lift off again for the return journey. But the size and mass of such a vehicle implied a launch rocket of almost unimaginable scale, beyond anything realistically achievable. Von Braun initially preferred a different approach: launch the lunar spacecraft in sections aboard several smaller rockets, assemble it in Earth orbit, and then send the combined vehicle to the moon. Even this left an unresolved issue: landing an enormous, fully fueled spacecraft on the lunar surface and then getting it off again. A NASA engineer named John Houbolt proposed a more radical idea, one that many senior engineers initially regarded as too dangerous. Instead of a single lander, 2 spacecraft would travel to lunar orbit docked together. The Command and Service Module, CSM, would be the main ship. It would house 3 astronauts, carry fuel, power systems, supplies, and serve as the vehicle for the trip to and from the moon. Attached to it would be a dedicated lunar lander, the Lunar Module, or LM, carrying only what was needed to descend to the surface, support 2 astronauts briefly, and then return to lunar orbit to rendezvous with the CSM. Because the LM was designed solely for short operations in lunar gravity, it could be relatively small and lightweight. That mass saving made it possible to launch the whole stack, CSM and LM, on a single heavy-lift rocket. Von Braun eventually endorsed Houbolt's lunar orbit rendezvous plan. But it came with a critical risk: docking, undocking, rendezvous, and the entire sequence of maneuvers in lunar orbit had to be mastered and executed perfectly. If anything went wrong, there would be no rescue. To build up the necessary experience, NASA embarked on 2 precursor programs, Mercury and Gemini. Between 1961 and 1966, 16 crewed flights taught American astronauts how to maneuver in orbit, eat and sleep in space, conduct spacewalks, perform rendezvous and docking, and understand the effects of weightlessness on the human body. Step by step, they were rehearsing the skills Apollo would require. Kennedy did not live to see those milestones. He was assassinated in 1963. But his lunar challenge remained the guiding objective for NASA. As the president himself had argued in his speeches, space was a frontier to be climbed precisely because it was difficult, and because the effort promised knowledge, prestige, and a measure of peace in a dangerous world. Even before Apollo flew a single astronaut, the program would face a catastrophe. In January 1967, the crew of what was intended to be Apollo 1, Gus Grissom, Ed White, and Roger Chaffee, climbed into their command module atop a Saturn IB rocket at Cape Kennedy for a ground plugs-out test, a full rehearsal of the launch countdown with the spacecraft sealed, fully powered, and operating on internal systems. Grissom, one of the original Mercury 7 and one of the most experienced astronauts in the Corps, was in command. Ed White had made America's first spacewalk on Gemini 4. Roger Chaffee was a highly capable rookie and former reconnaissance pilot. Apollo's spacecraft was extremely complex and had been developed on a punishing schedule. Test crews had already encountered coolant leaks, electrical glitches, malfunctioning environmental systems, and a maze of wiring, roughly 20 miles of it, packed into a confined volume. During the test, communications between the capsule and the ground kept failing, adding to the crew's frustration. Then, inside the sealed cabin pressurized with pure oxygen, something sparked. A short circuit in a cable bundle in the lower equipment area is the most likely cause, though the exact point of ignition was never definitively identified. In that high-pressure, oxygen-rich atmosphere, materials that normally burned slowly became violently combustible. Fire spread through the spacecraft in seconds. The three astronauts had no chance to escape. The inward-opening multi-piece hatch required tools and time to remove several bolts, and was effectively jammed shut by the pressure buildup inside. By the time technicians forced their way in from the outside, Grissom, White, and Chaffee were dead. They had not been lost in flight, but on the ground, on a test stand, with rescue crews only meters away. The shock was profound. Public confidence in Apollo collapsed, and internally NASA was forced to confront hard truths: rush design, inadequate fire protection, and a hatch that could not be opened quickly in an emergency. If Apollo were to continue, it had to change. The command module was redesigned into a safer Block II configuration. Flammable materials were replaced, wiring was rerouted and better protected, plumbing and environmental systems were simplified and hardened against leaks and shorts. Crucially, the hatch was rebuilt as a single, outward-opening unit that could be opened in seconds. The cabin atmosphere at launch would now be a nitrogen-oxygen mix instead of pure oxygen at high pressure. Suits, hoses, and interior fabrics were all reassessed for fire hazards. After a series of uncrewed test flights, NASA was ready to fly a crew again. Apollo 7, commanded by Wally Schirra with Don Eisel and Walt Cunningham, took the new spacecraft into Earth orbit in October 1968. It was a thorough, 10-day orbital shakedown, maneuvering, testing guidance systems, verifying life support, and practicing rendezvous techniques. The mission met its major objectives. Apollo had survived its first trial by fire and returned to crewed flight. The next leap would be far bigger. Intelligence reports in 1968 suggested that the Soviet Union might soon attempt a circumlunar flight, sending cosmonauts around the moon and back. To prevent another Soviet first, NASA made a bold decision. Apollo 8, originally planned as an Earth orbit test of the lunar module, would instead go all the way to lunar orbit without a lander. It would test the giant Saturn V rocket on a human mission, validate navigation and communications at lunar distance, and prove that a crew could safely enter and leave orbit around the moon. Commander Frank Borman, Command Module pilot Jim Lovell, and Lunar Module pilot Bill Anders became the first humans ever to leave Earth's gravitational neighborhood. Riding the towering Saturn V, over 110 meters tall and generating about 7.5 million pounds of thrust at liftoff, they climbed into Earth orbit and then fired the third stage again to head for the moon. After a 3-day coast, they fired their service propulsion system engine behind the far side of the moon, out of contact with mission control. When their voices returned over the radio, they were in lunar orbit. From just tens of miles above the surface, they photographed craters, basins, and potential landing sites. On one orbit, as the spacecraft rolled, Anders saw the Earth rising above the lunar horizon and captured the now iconic Earthrise photograph. A small, fragile, blue-white sphere suspended in the blackness above a stark gray landscape. It became one of the most powerful images of the century. Apollo 8's success, at the end of a violent and divided year on Earth, suggested that Kennedy's deadline might yet be met. But one crucial spacecraft still had not flown in its intended environment: the lunar module. Apollo 9, commanded by Jim McDivitt with Dave Scott and Rusty Schweickart, remained in Earth orbit but focused entirely on testing the LM, nicknamed Spider. After docking and extracting it from the SIVB stage, McDivitt and Schweikart undocked and flew the fragile, ungainly machine on its own. Designed only for vacuum operations, with spindly legs and thin walls, the LM looked more like an industrial construction than a sleek vehicle. It had separate descent and ascent engines, independent life support, and its own guidance system. On Apollo 9, the crew fired both engines, practiced rendezvous and docking with the CSM, and proved that the LM could function as designed. It was, in McDivitt's words, a real flying machine, even if it looked like it had been built out of foil. Apollo 10, with Tom Stafford, John Young, and Gene Cernan, took the final rehearsal step. After entering lunar orbit, Stafford and Cernan undocked in LM Snoopy and descended to within about 9 miles of the surface. They demonstrated the approach profile, tested communications and tracking in lunar conditions, and validated the guidance system close to the Moon. Then they fired the ascent engine and rejoined Young in the command module. Everything had now been tested, except the final powered descent and landing. Apollo 11 was assigned that historic attempt. Its crew brought together 3 very different but complementary astronauts. Neil Armstrong, the commander, was a quiet, analytical engineer and test pilot, known for his composure under pressure. On Gemini 8, he had already salvaged a life-threatening situation when a stuck thruster sent his spacecraft into an uncontrolled spin. Edwin "Buzz" Aldrin, the lunar module pilot, had a doctorate from MIT and was an expert in orbital rendezvous. He had manually guided Gemini 12 to a successful docking when automatic systems failed. Michael Collins, the command module pilot, would remain in lunar orbit in Columbia, responsible for navigation, rendezvous, and bringing everyone home. On the 16th of July 1969, millions gathered near Cape Kennedy and around televisions worldwide as the Saturn V carrying Apollo 11 thundered into the sky. 4 days later, Armstrong and Aldrin crawled into the lunar module Eagle, undocked, and began the powered descent toward the Sea of Tranquility, while Collins stayed in orbit. The landing sequence was tightly choreographed and heavily automated, but not everything went smoothly. During the descent, the guidance computer began issuing 1202 and 1201 program alarms, technical codes indicating that its processing load was momentarily exceeding capacity. In mission control, the guidance officer Steve Bales had to decide, within seconds, whether the computer was still performing its critical tasks or whether the landing should be aborted. Assessing that the overloads were transient and that essential functions were still running, he advised go, and the flight director accepted the call. As Eagle continued downward, another problem emerged. The spacecraft was being carried long, approaching a boulder-strewn crater instead of the smooth plane that had been targeted. Armstrong took manual control, flying horizontally at low altitude, searching for a safer patch of ground while fuel reserves dwindled. With less than a minute of fuel remaining, he guided Eagle to a gentle touchdown. "Tranquility Base here. The Eagle has landed," he reported, as cheers erupted in mission control. Later, descending the ladder to the surface, Armstrong delivered the famous line about a small step and a giant leap. For more than 2 hours, he and Aldrin moved carefully across the soil, setting up experiments, planting the American flag, taking photographs, and collecting rock and regolith samples. Collins orbited overhead, monitoring systems and performing his own observations, acutely aware that if something went wrong on the surface, he might have to return to Earth alone. Apollo 11 fulfilled Kennedy's pledge, but NASA's work was not finished. With the basic mission demonstrated, the focus shifted towards science and exploration, landing in more challenging terrain, staying longer, traveling farther, and bringing back more data and samples. At the same time, political enthusiasm and budgets began to decline. Apollo would have only a handful of missions left. Apollo 12, commanded by Pete Conrad with Dick Gordon and Alan Bean, had a critical technical goal: demonstrate a precise, pinpoint landing. Their target was Near Surveyor 3, an unmanned spacecraft that had landed on the Moon in 1967. If NASA could place the lunar module right next to this known point, it would prove that future missions could be steered to specific geological features. The mission almost ended before leaving Earth's atmosphere. Shortly after liftoff, the Saturn V climbed through storm clouds and the rocket plume triggered 2 lightning strikes that momentarily wiped out telemetry and knocked several systems offline. In mission control, warning lights flooded the screens. A young controller, John Aaron, recognized a pattern from a previous test and called up a solution: switch the signal conditioning equipment to an auxiliary mode. Alan Bean, in the right-hand seat, understood the obscure instruction and flipped the correct switch. Power and data returned, and the mission continued. Apollo 12 went on to achieve a near-perfect landing in Oceanus Procellarum, only a few hundred meters from Surveyor 3. Conrad's exuberant commentary on stepping onto the surface captured his delight at the achievement. The crew retrieved parts from the Surveyor probe, deployed experiments, and conducted detailed geological work around their site. By the time of Apollo 13, lunar missions were starting to feel almost routine to the public. Inside NASA, however, no one underestimated the risks, and this mission would prove just how real those risks remained. Apollo 13, commanded by Jim Lovell with Lunar Module pilot Fred Hayes and Command Module pilot Jack Swigert, who replaced Ken Mattingly just days before launch due to a medical concern, set out for the Fra Mauro Highlands, an area of ancient lunar terrain prized for its scientific value. 2 days into the flight, after an otherwise uneventful cruise, Mission Control requested a standard procedure: stir the liquid oxygen tanks in the service module to homogenize their contents and improve sensor readings. When Swigert flipped the switch, hidden damage from an earlier ground incident made itself known. A faulty heater relay and scorched wiring inside oxygen tank number 2 led to an electrical arc and a fire. The tank burst, and the explosion damaged adjacent systems, including the second oxygen tank. Pressure dropped rapidly. In the spacecraft, alarms sounded and gauges went wild. "Houston, we've had a problem," Lovell reported. Soon it became clear that the service module was crippled. Most of the command ship's oxygen supply, and with it much of its power-generating capacity, was gone. The only viable option was to shut down the command module to conserve its batteries for re-entry and move the crew into the lunar module Aquarius as a lifeboat. Its own descent engine could be used to adjust their trajectory around the Moon and back to Earth. What followed was an extraordinary improvised rescue effort. Engineers and controllers in Houston worked continuously to redesign the mission on the fly, computing new burns, balancing consumables, and inventing entirely new procedures to keep 3 men alive in a vehicle designed for 2 occupants for a much shorter period. One of the most pressing threats was carbon dioxide buildup. The LM's round lithium hydroxide canisters would not last for the extended return trip, and the spare canisters in the command module were incompatible in shape with the LM's environmental system. Using checklists and equipment inventories, engineers devised a way to attach square command module canisters to the LM system with only items available onboard: plastic bags, cardboard, tape, and an air hose. The crew followed the instructions, assembled the improvised adapter, and co-levels fell. Cold, exhausted, and heavily burdened with manual navigation tasks, the crew guided their crippled spacecraft back toward Earth. At the end, they reactivated the command module, jettisoned both the damaged service module and the LM, and braced for re-entry with no certainty that the heat shield or parachutes had survived intact. Radio blackout lasted longer than expected. Finally, Odyssey's signal returned, and parachutes appeared on schedule over the Pacific. All 3 astronauts splashed down safely. Apollo 13 never reached the Moon, but it became a classic case study in crisis management and engineering under pressure, a successful failure. Apollo 14 brought a familiar name back to the flight deck: Alan Shepard. A decade earlier, he had been the first American in space. Soon after, an inner ear disorder had grounded him, and for years he had served as chief of the astronaut office rather than flying. After undergoing a risky corrective operation, he was cleared to return to flight status and was eventually assigned to command Apollo 14, with Stuart Roosa as Command Module Pilot and Ed Mitchell as Lunar Module Pilot. The mission faced serious technical issues of its own. A docking problem between the command module and the LM had to be resolved in orbit. Later, a faulty abort signal threatened to trigger an automatic abort during the lunar descent. Engineers in Houston quickly developed a procedure to reprogram the guidance computer in mid-flight to ignore the spurious input. The landing radar temporarily failed, adding to the tension. Shepard and Mitchell nonetheless touched down safely in the Fra Mauro region, the destination originally planned for Apollo 13. On the surface, their work was scientifically productive and physically demanding. They traversed rough terrain, investigating craters and collecting a wide variety of samples. At the end of the mission, Shepard lightened the mood and made a small piece of cultural history by hitting a golf ball across the lunar landscape with a makeshift club fashioned from a sample scoop and a smuggled ball. The final 3 missions, Apollo 15, 16, and 17, represented the J-mission phase: longer stays, more advanced equipment, and a stronger scientific focus. The upgraded lunar module could support 3 days on the surface. Suits and backpacks allowed longer EVAs. A battery-powered lunar roving vehicle gave astronauts a range of many kilometers, turning landings into true field expeditions. Apollo 15, commanded by Dave Scott with Ol Worden and Jim Irwin, landed near Hadley Rill and the Apennine Mountains, a dramatically rugged site. Using the rover, Scott and Irwin explored the area and collected a famous sample of ancient anorthosite, nicknamed the Genesis Rock, thought to be part of the Moon's primordial crust, roughly 4.5 billion years old. Apollo 16, under John Young with Ken Mattingly and Charlie Duke, targeted the Descartes Highlands. Young and Duke spent 3 days on the surface, traveling long distances and sampling terrain that had been thought to be volcanic but turned out to be formed largely by impact processes. For Mattingly, relegated from Apollo 13 at the last minute, Apollo 16 was a delayed but well-earned journey to lunar orbit. Apollo 17, the last mission, launched at night in December 1972, lighting the Florida coast with the flame of the final Saturn V. The crew consisted of Commander Gene Cernan, Command Module Pilot Ron Evans, and Lunar Module Pilot Harrison Jack Schmitt. Schmitt, a trained geologist, was the only professional scientist to walk on the Moon. Their landing site, Taurus, Littrow, combined steep mountains and dark mare deposits and was chosen to maximize scientific return. Cernan and Schmitt drove their rover across nearly 20 miles of terrain, working long hours on the surface and gathering an extensive suite of samples. They deployed instruments, documented layering in crater walls, and helped refine theories of lunar history. After 3 days, it was time to leave. Climbing the ladder for the last time, Cernan offered a brief farewell and expressed the hope that humans would one day return with peace and hope for all mankind. As of now, no one has walked on the Moon since Apollo 17. After the program ended, NASA shifted its focus. In 1973, the last Saturn V launched Skylab, America's first space station. In 1975, the Apollo-Soyuz test project marked a symbolic thaw in the space race, as American and Soviet spacecraft docked in orbit and crews conducted joint operations. The space shuttle era began in 1981, promising reusable spacecraft and a new approach to Earth orbit operations. Yet the legacy of Apollo, the engineering lessons, the scientific data, and the cultural impact of seeing Earth from another world, endures. Today, NASA's Artemis program aims to return astronauts to the lunar surface, including the first woman and the first person of color, and to build the capabilities needed for human voyages to Mars. The path blazed by Apollo, with all its achievements and tragedies, remains the foundation on which those future journeys will be built.